So now let's tackle logarithmic functions. The logarithmic function with base a for positive real number a is log, and then you put a little a down here, of x. It is the inverse of a to the x. So log and exponential functions are inverses of one another. If I tell you that it's got an inverse, then you know it must be 1 to 1. Now I'm going to encode this information with the following equation, and I'm going to call it the exponential form of a logarithmic equation. And this is just a nice sort of Rosetta Stone to go back to. So if I have log base a of x is equal to y, this is the same as just another way of writing a to the y equals x. So to state this using sort of inverses, a raised to what number gives me x? That number is the log base a of x. That's the definition of the log base a of x. This a is looking a little bit like a 2. Let me just clean that up a little bit. So let's do some quick examples. Log base 2 of 8 is then 3, and that's because 2 cubed is 8. All right, so log base 2 is a function. The input to that function is 8. The output is 3. 2 to the x is a function. The input of that function is 3. The output of that function is 8. So we see those are inverses of one another. Okay, let's do a heavier example. Solve for x. We've got log base 3 of x minus 2 equals 4. So what I want to do is I want to rewrite this as an exponential equation, because I know how to solve exponential equations. So I'm going to convert to an exponential equation. So I write the equation, the original one, log base 3 of x minus 2 equals 4, and then I rewrite this in the exponential form. So how did this go? Well, the base got raised to this power. So 3 is going to get raised to the 4th power. So I write 3 to the 4th, and that's equal to what? Well, if I have the base raised to the right side, so base raised to the right side, that's equal to the previous left side. So 3 to the 4th should equal x minus 4. Continuing, 3 to the 4th is going to be, well, 3 squared times 3 squared, that's 9 times 9. So 81 equals x minus 4. If I add 4 to both sides, that tells me x equals 85. And that's my final answer. And if you want to, oh dear, I slipped a, this should have been a 2, not a 4. This should have been x minus 2, not x minus 4. I literally just slipped the symbol. X minus 2, adding 2 to both sides gives me 83. So if you want to plug this back into your calculator, you'll get that. So we can also just kind of step backwards, and it should make sense. I was looking at 85, I was like, that makes sense. If we take 83 and plug it into the original equation here, it's going to be log base 3 of 83 minus 2. Well, 83 minus 2 is 81, so log base 3 of 81 is going to be 4, because 3 to the 4th power is 81. All right, let's do another one. Again, sorry for that little typo there. Let's try, just because this is a little bit confusing for some people the first time they see it, let's try to do another equation kind of like that. Solve for x. Let's do log base 8 of x plus 1 equals 1/3. Oh, I guess I should point out, so we know that this is the inverse function of an exponential function, and exponentials can never be negative. So therefore, the input to a logarithm is never going to be negative, right? There's no number I can raise a real number to, no real number I can raise a real number to, and get a negative number. Sorry, there's no real number I can raise a positive number to and get a negative number. So for that reason, the domains of a logarithmic function are always going to be positive. And when we graph these, you'll kind of see that in action. So what I want to do, solution, I want to convert this. So I write the original equation, and this is log base 8 of x plus 1 equals 1/3. And now I want to convert this to an exponential equation. So this is now 8 to the power 1/3 equals x plus 1. Well, 8 to the power 1/3, that's the cube root of 8. 8 to the power of 1/3 is 2, so 2 equals x plus 1, which tells me that x equals 1. And that's my final answer. Okay, so the basic trick here is to use this thing that I called the exponential form of the logarithmic equation. That's really the trick, because we tend to know how exponents work, and sometimes we're a little confused as to how logarithms work. Right? So let's now move on. I want to tell you about a special number and a special logarithm. So there's this number e, and this is roughly equal to 2.71828.182845945, etc., etc., etc. And it's, you can think of it as kind of like pi. It's one of these really important but weird numbers. It's irrational, so it has a non-repeating infinite decimal expansion, and it's just a really important number. It's a little tough to see its importance just yet, and because of that, and because it's such a weird number, some people prefer to not teach it to students until after they can really appreciate the importance. And so this is called a transcendental approach, because I'm showing you this transcendental number e. Transcendental has something to do with, it can't be the solution to any simple algebraic equation. And then there's the non-transcendental method, which would be postponing the introduction of e until, sometime during or after calculus. So we can have the exponential function e to the x, and this is, if someone says the exponential function, or if you just see exp of something, sometimes you'll see exp of x. That's e to the x typically. And it has an inverse, so log base e of x. We write this as ln of x, and this is called the natural log. So oftentimes we'll see the natural logarithm pop up. So the using this, it's just the same as using any other positive real number to do anything else. But using this, I can introduce what we call the laws of growth and decay. So the laws, and the book is going to separate these out, and it's going to have the law of growth and the law of decay. I like to just put them together and have you remember a minus sign. So it's a little bit different than the way the book does it. You can follow the book's presentation, and that's fine, but I just like to put it together. Laws of growth and decay. State that the growth or decay of an initial quantity, which I'm going to call Q0 or Q0, after time t with rate, so I'm going to say rate r, and r is positive if it's growth, r is negative if it's decay. And notice if r was 0, then it's going to neither grow nor decay. Gives us a quantity of, and I'm going to write q equals q0 e to the rt. So this is the law of growth and decay. The book is going to separate it into the law of growth when r is positive and the law of decay when r is negative. This is basically just a type of formula you'll see in a lot of different places. If we were talking about continuously compounded investment, then this Q naught would be the principal, which we would denote by P, and that's going to give us PERT. Okay, that some of you have maybe seen. So let's do a couple of examples of this, and then we'll leave it. So in my old apartment, I found a mold that grew with a daily rate of 0.42. And then I just eyeballed it. I was looking at it and I was like, oh, that's probably a daily rate of 0.42. Also, this rate, we need to specify the time. You know, it's like if I tell you how fast a car was going in miles per hour, you know, and I use some number, that's going to be a different number than if it was feet per second, right? So this rate, you should give the units for the rate. So a daily rate of 0.42, if there were 20 milligrams of mold on the first day that I noticed it, how much was there after 10 days? Okay, so I don't know about you, but when I see a problem, I'm like, I'll get on that right away, which means, you know, about a week and a half. So we're going to say 10 days. Okay, solution. Again, like I've been saying since day one, I really like for you to start your solution by writing down the equation. Q equals Q naught e to the RT. Not only does this help you reinforce your understanding in that you can link these formulas to these types of questions, but it helps you remember the formula. Moreover, I like having everything laid out so I know where to plug things in. So I'm just going to plug things in. Well, the initial quantity was 20 milligrams, so 20 milligrams. Then I've got my magic number E, and then I've got my rate of 42, so 0.42. And then I've got my time. How many days was it? Well, 10 days, 0.42 times 10. And my final answer, without using a calculator, is going to be 20 times e to the 4.2 milligrams. Okay? And this is where you can leave it because I don't want you to use a calculator. All right. Now, if if for some reason I'm giving you a quiz or an exam where you have a calculator or something, then you can plug this in. But for our purposes, you know, for the purposes of giving me an answer on an exam, this is enough because I don't want you to worry about typing a bunch of stuff in. Now we notice if we type this in on a calculator, we should get, so 20 e to the 4.2 should be roughly 1337.7 milligrams. Okay, just as a side note, and that's because the next problem is going to use that. So one more example. After these 10 days, I sprayed it with mold killer, and it decayed. Of course, this is the rate on the size of the bottle, on the side of the bottle, at a rate of negative 0.62. How much was left after a week of decay? And I'm almost certain this is not how mold killer works. This is just something where I could set things up in a fairly straightforward way. So again, solution, I want you to start by writing out the equation. So Q equals Q naught e to the RT. We just plug things in. So Q naught, the initial amount, was now the end of the previous question. And this is one of these like rolling information things. I will normally, in like a quiz or an exam, I will try to avoid this. I'm just doing this because this is kind of like an application section. But on a quiz or an exam, if you were to make a mistake up here and then that mistake would percolate through down to here, that would be sort of double jeopardy for you. I don't like doing that if I can avoid it. But for this question, just for a special example in the lecture, we have 1.337 times 1.337.7 times e to the negative 0.62, and then times 7. So that's going to be 7 days because it's for a week. And I will even, and I'm kind of just trying to demonstrate, I will even let you leave it here like this, because I know you can go over here to the side and you can do 0.62 times 7, and you can work this out without a calculator. 7 times 2 is 14, then we've got 43, and so this should be 4.34. I'm sure you can work this out on a calculator, but I don't need you to do that for this class, okay? I'm confident you can do that kind of stuff on your own. If we were to type this in, I think we're going to get something like 17.4 milligrams, so we see that we have almost gotten it back down to where we were when we started. And there's still a bit more in this section,